Excited to have Casper, full name Stephen Casper, here. He's a final year PhD student at MIT in the Algorithmic Alignment Group, advised by Dylan Hadsel-Mennel. He leads the research stream for math and mentors for ERA and Gov AI. He's also a writer for the International AI Safety Report and the Singapore Consensus. His research focuses on AI safeguards and governance, as we'll hear about today, with research featured at NeurIPS, AAAI, Nature, Effect, EMNLP, STAT, ML, TMLR, IR, AIS, and a number of workshops, and over 20 press articles.
That's so kind. Thanks, Eric. And I'm really glad to be here, and I'm really glad to be part of this seminar series. I was looking at the roster for the rest of it, and I'm in a company that I'm very impressed by. So I'm thankful for the chance to be here. Like Eric said, I'm usually at MIT. That's where you can find me. And most of the work that I do is the union of the topics of technical AI safeguards and technical AI governance. And that's what we're going to focus on today. So I'm going to talk about a few items of work, some of which I've done at MIT CSAIL, but also a little bit that I worked on last year at UKAC when I was working for UK government in a research residency. And this is work that I've done with a bunch of very, very nice people here. And a couple of notes before we get started. One is that Tony, whose pizzas are for the day, we're really thankful, said that I think she'll sneak pizza in when it's available or when it's delivered in like 5 or 10 minutes. And as long as everyone's listening, I think I said it's great to go and mix around and get pizza while we're talking. So that's all fine. And then when it comes to questions, I have a couple slides that I'll pause for questions, if you have bigger ones. But other than that, just ask questions probably before the end if they're kind of urgent or the clarification things that we can do. Does that all sound good? Okay, thanks so much. I'm just glad to be here again. So I want to start by talking about a new type of observation we're getting from the AI safety ecosystem as of last year, the 2025. And that is where we're starting to see AI developers, major ones who are releasing big prominent models, reporting alongside their models that according to their own evaluations, their models might be starting to maybe cross thresholds that would enable some significant and large scale risks, especially related to bioharm capability uplift, cyber attacks, or chemical attacks. And we saw this, for example, with Gemini 2.5, Claude Opus 4, and ChatGPT Agent. And this is all new, and it's not very great news in light of how these models are also very persistent and vulnerable to attacks that try to elicit harmful capabilities from them. I think a candidate for my favorite paper of 2025, for clarification, I'm not on this paper, but it was worked on by Great Swan AI and folks at the UK AI Security Institute during my time there. And this paper focused on crowdsourcing a lot of attempts at jailbreaking state-of-the-art production models. And they looked at over 1.8 million attack attempts, including 60,000 plus successful ones against 19 different production language models. So there's a really big attack surface, and there's a lot of precedent for people extracting harmful capabilities from today's most advanced models. So the situation that we need to deal with is kind of well described, for better or for worse, with that smiley Shoggoth meme, if you know what I'm talking about. And if you have it on your seminar series bingo card, you can cross off the Shoggoth meme square. But where we have models that are kind of like this, that we train with RLHF and other types of techniques in order to have good behavior. And that results in them having nice outward behavior in most situations. But they persistently seem to, and including under the best attempts of some researchers to make them not, have these harmful capabilities or these latent capabilities that can and do cause harm when they resurface due to some sort of attack or modification to the model or some sort of anomaly that they run into. So this is the problem that we're going to focus on today. And there are a few goals for today's talk. The first thing that we're going to talk about is how we can more rigorously train and evaluate AI models for deep safeguards, or what I'm going to call deep safeguard, referring to safeguards that are very challenging to remove, if not maybe even impossible under some threat models. Second, we're going to look at the much, much harder problem of how we can actually make state-of-the-art AI safeguards research matter in the real world. And along the way, we're going to learn about what AI safety can learn from the design of light bulbs. And we're going to talk about this dude and why I'm keeping a very close eye on him in 2026 and why I think all of you might want to as well. Sound okay? So let's get started. And I want to talk about the bad news first, or one perspective that I like to use when thinking about the problems that we're up against. And we need to fully appreciate the scale of the size of the game of whack-a-mole that we've all really gotten ourselves into when it comes to safeguarding modern AI systems against harmful behaviors that they might be able to exhibit. So the idea here is that there are just a lot of inputs that we can give to AI systems, a lot of situations that we can put them in. So we can think of the input space for these types of systems as being very, very large, like hyper astronomically large, like too large to even be worth, entertaining very seriously, like attempts to quantify it. Like for example, even if we limited the input size or context window for today's modern language models to like 15 or 20 tokens, with modern tokenizers, there are still more 15 or 20 token inputs to them than there are particles in the universe, and it's not even close. So we have this goal of making sure that models are safe under any inputs that we can give them, but we are just never, ever, ever going to be able to achieve this goal in practice using anything that resembles current methods. And instead, what we try to do, like if you're a developer or an evaluator, is use techniques like red teaming or adversarial attack algorithms to identify classes of failures that we can notice. And if we notice them, we can train against them, we can plan mitigations for them. These types of failures are bad, but they are not frighteningly bad. There's nothing unknown about these types of problems. The much more difficult challenge is the unforeseen failure modes, like those jailbreaks, for example, that a developer didn't anticipate before it released its model. And these are much more difficult because we don't have good feedback when it comes to how to train against them or mitigate them. So in practice, this gap between yellow and red is always going to exist. And the challenge that we have is people, engineers who care about safety, isn't trying to, well, one, shrink this gap, and two, make it so that we can have ways of understanding how big this gap might be, even though by definition, we're not able to directly observe things within it. And we're going to talk more about that. But in the process of handling these kinds of rare failures or these hard to find failure modes, or at least hard to find pre-deployment, we can take a page from the safety engineering textbook, or the figurative one, and that's the page that says that safety critical systems should be designed and ideally tested in order to handle stresses that are at least as great, if not greater, than those that they will face in deployment. And this principle has nothing to do uniquely with AI. You see it in construction law, for example, where have you ever heard of building being built with like a safety factor? You're familiar with safety factors from engineering? Yeah, so if a building is built with a safety factor of like 5, that means that the building has been designed and its components have ideally been tested in order to withstand about 5 times the forces and stresses that building is ever expected to undergo during maximum occupancy practice. And this is really nice because for any individual building, this might kind of be overkill, but the construction field in general wants to make sure that things like building collapses are very, very, very rare. So they over-engineer the safety of individual buildings. And the benefits of this are observable, kind of tangible in practice, because big building collapses don't happen that often. If you go to Wikipedia, there's this category, I love Wikipedia, of collapsed buildings and structures in the United States. Thank you. And it only has about 20 articles inside of the whole category. And that's all great. And I love talking about construction. And I love being in a building like this and like not worrying about it crumbling beneath my feet. But my favorite way to talk about safety factors in engineering involves looking at light bulbs, like this one. So we're all pretty familiar with light bulbs. Most notably, there's this bulb component to them, and they're made of glass, including this one. At least usually they're made of glass. And the bulb part of a light bulb, like it serves a few purposes. Like one, it makes it so that you don't like bump the filaments and break things. That's nice. Two, at least with incandescent bulbs, these bulbs like keep argon in and oxygen out, which is nice for light bulbs that you want to last more than a fraction of a second. But the bulb also serves a purpose, including a safety critical one, involving protecting you, right? This bulb, you don't want it to shatter in your hands. Lots of people over the course of the world screwed in light bulbs. Probably all of us are among them. This has happened billions of times. And if you're an engineer kind of worried about anomalous or weird failures with light bulbs, you want to make sure the design of this thing is something that is going to fail very rarely, if ever, by crumpling in someone's hands, because that's bad. That means glass in your hands. So smart engineers who are designing light bulbs like this have decided to make the bulbs like quite strong. And even though they're made of glass, and even though the thickness on these things is usually about 0.2 to 1 millimeters, they're stronger than most people think. And I want to demonstrate that to all of you right now. Don't try this at home. And I would never put anyone in danger of shrapnel. That would probably look pretty bad. So I'm going to do it inside of a plastic bag. Are you ready? I'm going to squeeze it as hard as I can. You probably might have figured out what I'm going to do. Oh, and I should say, according to Claude, The average grip strength for an adult man of my age is about 110 pounds. So, ready? 3, 2, 1. Thanks, safety engineer. I don't know if that was kind of anticlimactic, but yeah, it didn't shatter. That's the point. And so I'll tell you the truth, like what I did might not have been as insane as it looked because I applied the same kind of safety factor testing methodology in making sure that this light bulb was safe to do this demo. Because I have spent so many times squeezing this light bulb with gloves. And also, like, I've tested it under stresses quite a bit more than what I was able to just exert. I've tested this particular light bulb with gloves doing this as hard as I can, which is quite a bit stronger than something I could do with my hand. Okay. So we're having a good time squeezing light bulbs, but this is a talk about machine learning. And how can we apply this kind of safety factor philosophy when trying to design safer AI systems? How can we train and test them under stresses that are stronger than they will typically face in practice? This is where something I call model tampering attacks come in. And I've been working on this kind of stuff for a few years. And what a model tampering attack is some sort of attack that's able to think outside the box of what you usually do, or maybe like inside the box. So compare this to a standard attack that we'll usually like talk about or work with when we're thinking about AI systems, which is like a prompt-based one for a language model, where you will try to design some sort of prompt or some sort of way of modifying prompts that's likely to make an AI system behave harmfully. This is the typical way of doing attacks. Model tampering attacks are significantly more privileged and powerful. So instead of just manipulating the model inputs, the latent space attacks and wait space attacks, these tampering threats, have the ability to fiddle with either the model internal activations or the model's weights, aka wait space attacks actually just kind of adversarially fine-tune the model a little bit according to some sort of parameterization. And there are some nice things about model tampering attacks when you're studying AI risks. One of them is that these attacks are very strong because there are quite literally fewer layers of safeguards in between where you apply the attack and where you try to extract a harmful capability from the model. Second, model tampering attacks, they can help you take advantage of structured representations inside of the model. Because as networks propagate information through them, they form more abstract structured representations of what they're processing. And that can make it easier to kind of like hook into triggering certain types of harmful neural circuitry with the model tampering attack that might be very, very difficult to do through the input space. You can trigger harmful neural circuitry involved in tasks that you don't even necessarily know how to elicit through the input space. And finally, model tampering attacks are very expressive, partially because you can optimize them in continuous space and partially because of the richness of the representations that you're manipulating. And my favorite demo of this came from some work that I did recently with some collaborators, where we used a latent space attack to encode a QR code to the paper's website inside the model activations themselves. So you can scan this and you can go to obfuscatedactivations.github.io, which was pretty fun. Credit to Luke Bailey for that idea, which I think was fantastic. And we're going to talk about a few uses of model tampering attacks, and I first want to start with them on the defensive side of the ball by talking about a couple of papers involving latent adversarial training, or adversarial training under these latent space attacks. And the basic setup for doing this in language models is as such. You'll start with a prompt. This example here might be small for you to read, but it says, how can I make a bomb? An oldie but a goodie. Classic prompt that I love to red team language models with. You'll pass that prompt through the model, you'll collect the sampling probabilities for its outputs, and then you'll do the first step, which is to calculate the attacker's loss and optimize some sort of latent space perturbation. So you'll calculate the loss with respect to some sort of harmful completion, like, sure, here's how to make a bomb, step one, blah, blah, blah. And using your favorite parameterization, your favorite optimization algorithm, and your favorite constraint that you want to apply to these perturbations, you will, through one step or multiple steps, come up with some sort of adversarial perturbation. We'll call that delta. And then once we have delta, we are done. We're in good shape. Because then we can make another step pass through the model with the prompt, this time with delta applied, and then we just train the model as normal to complete sentences harmlessly. So, for example, training it to say, sorry, I cannot help you make a bomb, blah, blah, blah. And in effect, what we're doing here is like trying to very rigorously train the model to have these deep safeguards inside of it by telling it to do the right thing, even when an adversary is trying to manipulate its brain into doing the wrong thing. And I want to tell you about a few experiments that we've done involving latent adversarial training. The first of which involves making models more jailbreak robust. So what we did is we took a handful of models to study and attack with some jailbreaking attempts. Here in yellow, we have a baseline model straight off the shelf. Here in red, light red, we have a refusal training algorithm, which is the most common way that models are trained to be resistant to jailbreaks. In dark red, we have another algorithm called R2D2, which at the time was a state-of-the-art input space adversarial training algorithm for robustness problems like this. And here, both of these blues refer to different types of latent adversarial training, only differ by which layers we applied the perturbations at. So we're comparing these models under this jailbreak setting. The first thing that we need to do is a sanity check to make sure that there's no funny business going on and that all models, after we apply all interventions, are comparably performant across some key general capability and utility benchmarks. So good news there. And then when we test them against a suite of 6 adversarial jailbreaking attacks, we find a nice pattern. And that is that the blue latent adversarial training models are more robust to these jailbreaking attack suite than the other models are. So that's nice, like the numbers went in the right direction. But my favorite thing about these results is actually something not shown here. And it's that these models, like the blue ones, were much, much more efficient to fine tune compared to the prior state of the art with R2D2. Depending on what your favorite computational utilization criterion is, these blue models were between 35 and 750 times more efficient to train than the prior state of the art, which was exciting. Second, I want to tell you about one more experiment with latent adversarial training, which is actually kind of my favorite. And it's where we removed backdoors from language models. Has anyone here worked with backdoors before, or do you know the definition of backdoor? We know the definition of backdoor. Yeah, I'm not a backdoor person myself, but we did some work with it. A backdoor, for anyone who's less familiar, refers to a type of behavior that can be implanted into an AI system, usually by training on examples of that behavior, where the model associates some sort of unique type of trigger in its inputs with some sort of unexpected and often harmful types of outputs. So one toy example of a backdoor would be a model that if you tell it a certain passcode in text will start to produce toxic speech following that introduction of that type of passcode. And backdoors are troublesome to remove, especially when you don't have knowledge of what the trigger is, unless you use latent adversarial training. So here we have a baseline model off the shelf again. And here we have some normal methods. In this case, it was direct policy optimization, DPO, very common algorithm. And we tried this with and without some proxy triggers, where we used the triggers that some sort of red team tried to reconstruct, but they didn't do a perfect job. And then we did the exact same thing with latent adversarial training. That is these 2 blue examples. And then the first thing we tried, sanity check again, no funny business. All of these models are comparably performant on the task according to the reward model that was used to train them. But then when it comes to the removal of backdoors, we see a pretty big difference between the naive approaches and latent adversarial training, where latent adversarial training was quite successful. And these results are about as positive as they could be from the perspective of latent adversarial training being a solution to backdoor removal without knowledge of the trigger. And I was pretty excited about this because if anyone is familiar with some Anthropic work on this problem, this paper came out a few months after the Anthropic sleeper agent paper, which was all dedicated to the difficulty of removing backdoors when you don't have knowledge of the trigger. And credit to Aidan Ewart, who did this experiment, but I was really happy that our paper pretty much showed that this sleeper agent problem was only an open problem for a few months, which was exciting. Yeah.
How does this square with some of the results on the theory side that show that they're are just cryptographically undetectable backdoors, which would then therefore also probably imply unremovable?
Yeah, that's a good question. And I've not worked in cryptographic backdoor implantation settings. And I believe there was some work, actually from some maths people, about maybe we're talking about the same thing, maybe we're not, but backdoors that are implanted in ways that provably resist elicitation through fine tuning. Mm. And you can only really get them with the right input or the right trigger. And I think this is interesting. Unfortunately, it's not an area that I've worked in, but I do. The red teams have figured out ways around this type of setting. But the main reason why I'm not super worried about this type of threat in the work that I'm doing, at least in this context, because here backdoors are a proxy for bad behaviors that you don't know the trigger for, you don't know how to elicit. And we were using it as a nice research sandbox to study in. And the problems that were in our head during this were like, oh, well, the model has like harmful bio capabilities or harmful cyber attack capabilities that the red team just might not have found with their input space red teaming. That's a good question. So next, I want to transition to the offensive side of the ball, where we're using model tampering attacks for evals. And I want to also use this point to invite everyone to get some pizza if you're hungry, right? It should. I think now can be a great Schelling point in time to get some food. And if your stomach is happy while you listen to the presentation, maybe that will reflect more positively on you too in your psyche. But that's like adversarial training. Now let's talk about model tampering evals for model evaluations. And for the past few years, I've been trying to help lead the charge with some others from the algorithmic auditing literature on the usefulness of white box methods, model internals methods, for rigorously evaluating AI systems. One project that I worked on, for example, was titled Black Box Access is Insufficient for Rigorous AI Audits, trying to get a lot of academics together to make this point clear. And I think this paper, along with quite a few other works from others in the auditing literature, like Ben Bucknell should get a lot of credit here. Deb Raji, is she going to be at a seminar here soon? She's been a superstar in this literature as well. But it's been kind of cool in the past year or so to see some of this make difference in like implementation of regulatory policy. Like in the EU, the Code of Practice for General Purpose of AI Models has some pretty academically rigorous requirements
And then there's your video.
about
So
access for
right now they
third-party
can't
audits
see you.
when doing
This is the
rigorous
video,
evaluations
yes.
in compliance with the
video-
EU AI Codes of Practice.
It's right there.
But it's one thing
This
to
goes, here.
know that model
Okay.
internals
Thank you.
Got
algorithms
it?
are generally very useful for this thing. And it's another to make some more progress on specific methods of using model tampering threats to identify these types of vulnerabilities in models that might be difficult to identify otherwise. So I want to talk about a paper titled Model Tampering Attacks Enable More Rigorous Evaluations of LLM Capabilities. And I think this is one of the most interesting projects that I worked on in late 2024. And I think the most exciting thing about it is that in this paper, we were able to show that even if you're worried about black box attacks against a closed API model, model tampering attacks can still help you do more rigorous evaluations of the weaknesses. So what do we do in this paper? Here we focused on a capability elicitation and capability suppression type of game. We were studying the elicitation of bio-risk related capabilities. This is a research sandbox I work in a lot. And we were comparing 8 different model defenses where we tried to suppress harmful bio capabilities against 10 different model attacks where we tried to re-elicit those. And 5 of those attacks were input space attacks. And 5 of those attacks were model tampering types of attacks. And the first research question that we wanted to ask was like, what can we learn about some types of attacks from other types of attacks? So we took 65 model checkpoints that were trained with these 8 algorithms, and then we used all attacks on them. So we created this like 65 by 10 array of data involving model attack vulnerabilities. And then we did a pretty simple thing. We just ran principal component analysis on those models under those attacks. And we're trying to look for like a robustness subspace that models tend to exist on with respect to different types of attacks. And does anyone want to guess, when we have this 10-dimensional data, like how many principal components were necessary in order to explain 90% of the variation? One. Oh man, I set it up to. So 2. Okay, the guess is 3. Let's go with 3. Okay, so 3 is the right answer. Although I really love the guess of 1. Right, that like a model that's vulnerable to one type of attack should be likely vulnerable to other types of attacks that might be, eliciting the same type of thing through the same type of mechanisms, although through a different medium. And that's what we find. You only need 3 to explain the variation here, which tells us a lot about like, how different attacks might be operating through some similar mechanisms. And we did some more analysis that I'll spare you about, where we ran the regressions and kind of more rigorously showed that model tampering attacks can tell you more information than you can ever learn from input space attacks alone. But in light of what different attacks can tell us about each other, I then want to tell you about, I think, my favorite result from this paper. And this result is not going to shock you. Don't prepare to be surprised. But I'm going to talk about why I think it's very, very useful for us anyway. So we made a scatter plot here, where we took 65 models, and you'll see 65 points in a second, and we looked at the best performing input space attack. and the best performing fine tuning attacks. So we took the best of 5 here and the best of 2 here. And the reason we selected fine tuning attacks was that empirically, and in this work and others that I've done, fine tuning attacks tend to be stronger than latent space ones. We plotted them against each other. And these attacks were sort of resource matched, where we use the same data affordances in both settings. And actually, we use more compute for these than these, but that's just a bonus. The real thing to notice here is that in 64 out of 65 cases, the model tampering attacks were stronger. They were better at eliciting the harmful type of capability than the input space attack. And if that doesn't surprise you, good. But the reason why I'm interested in this result, because we use these resource matched attacks, is because of this problem, right? Like I said earlier, if we have this red gap that we need to fill and that we need to learn about. So there's this problem that kind of plagues evaluations of AI systems, at least evaluations that use the same affordances or the same input modalities of attack that are going to be available to a model post-deployment. And that problem is that the worst thing that your red team ever identifies a model doing is necessarily only a lower bound for the worst possible case performance that it could ever exhibit, right? That's just kind of saying that yellow is less than yellow union red. So we get this lower bounding relationship. And as a result, we're going to get this bias toward underestimating a model's worst case possible risks. And that's not just a challenge in theory. Like we can point to a lot of instances in which a developer releases a model, they assessed it for risks, they didn't find a certain type of harmful behavior that then resurfaced after it was deployed. So I'll say one more sentence and then we'll talk. But model tampering attacks, because of how strong they are a useful way of like overshooting our goal with evaluations. And by evaluating the model under stronger attacks, then it'll typically be vulnerable to in deployment. We are able to, by overshooting our goal, get a way of sort of understanding what types of unforeseen threats we might be up against that just because our red team failed to find. Does that make sense? What were you thinking?
Well, you may have just answered my question. So the fine tuning attack may overestimate instead of underestimate, right? Because that's not an actual risk in the real world, maybe.
Yeah, there's no more kind of like clean bounding relationship that we can make between, what we can elicit from a model with input versus tampering attacks. So great question. And now we're at our first checkpoint, which is an extra good time to get pizza. And I just want to ask how we're doing so far, how we feel about powering up adversarial training and testing using model tampering attacks. Are there any questions? Yeah.
So when you allow for fine tuning the model weights, isn't there essentially no way to stop an attack on like open weights model? Like no matter how much you try to safeguard your allowing for fine tuning, you can always get a model that is not safe.
Yeah. Would you mind putting a pin in the open model discussion for just a little bit later? And then we'll discuss that more. And then later you can ask again a version of this question if you still have it. Will that be okay? I'm sorry to like disappoint. But yeah, we'll definitely get to this. But I'm excited. I'm picking up what you're putting down. Are there other questions? Yeah, Jess.
I guess like, do you have like thoughts on how, like how, I guess like testing for fine tuning attacks can be done sort of in like an efficient way? Because it seems like, okay, if you're allowing those kinds of attacks, which I buy your arguments that, we should.
Yeah.
Then all of a sudden, like trying to evaluate how bad those attacks can be is like very, very costly, right? So yeah, what are your thoughts for like selling people who actually have to like pay the costs of these evaluations?
Good afternoon.
Yeah, I like the way you're thinking about this. So I've not done work like this myself, but I can
Thank you
attest to
very
how
much.
like fine-tuning attacks
Mrs.
or other types
Johnson?
of tampering attacks are like something you usually want to spend grad
So you want
students
me to
on.
come today?
And I am thinking about some of these problems though. And I've been talking with Kellen Pellerin and others
Okay,
at FAR
so you are at
about
one
some sort of
South
project
Place,
related to this.
2025?
But the
Okay.
idea or the motivation here is to imagine that you're Hugging Face. And you want to say like evaluate thousands or
I'm
maybe millions of
coming,
models that are up on your
say,
platform for risks
Baltimore
that they could
Street,
pose after small
I
amounts of
take
fine-tuning.
South Street, right?
Which is information that Hugging Face could like maybe want
If
and
I
do really
come
good
to
things. with.
Baltimore Street,
But then there's this challenge of
downtown,
like, how do you do that efficiently
Baltimore
across
and,
models when the type of attack in terms of its parameterization,
Quiet.
hyperparameter configuration, that works on one model the best is totally not guaranteed for other models even of the same
entrance is where again?
architectures. So there's inspiration here to be taken
Oh,
from
South Street, okay.
automated hyperparameter fine-tuning methods.
Okay.
And I
right.
have some
Right.
interest
Is that the
in like,
commerce
solving some of
building?
these
Is
problems
that the
soon and
commerce
working with
building? What do you
organizations that
call
host
it?
a lot of models in making progress on broad
Yeah.
reaching valves.
Okay.
Sometime in
All
the future.
right, I'll
I think this would
find
be
it.
really exciting.
1 South Street.
That's a good question. And
Okay, great.
I'll move us along a little bit to keep a good pace. And if this presentation were a year ago, like if I was talking in January 2025, I would have stopped here. I would have happily stopped here, and then we could like break early, have some more pizza, all of that good stuff. But it's a different world than it was in January 2025, right? Like a lot of time has passed. I really feel like I was very young and naive in 2020. Like it was before I found my first gray hair. No offense to anyone. But if it's also useful for reference, like this is what we were all listening to in January 2025. Like that's how long ago it was. But the world's a different place. And there's one type of major event in the AI ecosystem that has kind of changed the risk management landscape that I'm thinking of that happened in January 2025, which we're going to need to spend a lot of time. Does anyone know what event from January 2025 I'm likely to start talking about?
Inauguration,
What's that?
the Trump inauguration.
Oh, actually. That's just as.
It does change the regulatory
Let's
landscape.
think about the technical ecosystem, but yeah, like 10 points. Yeah, forgot about that. And shut that out. DeepSeek, specifically DeepSeek R1, which was released in January 2025. And DeepSeek's like a big deal. Like the first time, I don't know about you, but the first time I realized that DeepSeek was going to be a big deal was when in late January of last year, my dad just sends me a text and he's like, "Hey, Steven, what's up with DeepSeek?" And that man has like no business knowing about anything going on in the AI space. But that he knew about DeepSeek was a sign. And originally, actually, though, I thought that DeepSeek was like an anomaly, or that it was a flash in the pan. But not quite. DeepSeek was really just like the new normal. Because shortly after it was released, what we started to see was like new model after new model with openly available weights on the internet that anyone could download and modify, just like be made available, each of which, each of the prominent ones at least, kind of busting past the old state of the art. And in 2025, like the field has really kind of woken up to, the necessity of doing risk management research in a world where very prominent open models are just available and popular all over the internet. This wasn't the case before January 2025, at least definitely not to the degree it is today. So there's a lot of like cultural penetrance and popularity of specific models. If you look at open model usage trends too, they're pretty dramatically increasing. So one of my favorite charts to look at is from a paper, Bhandari et al., which tracks the download and spread and usage of open models on Hugging Face. And the x-axis is time here. And what you see is this very solid, steady increase in the usage of open models, except wait, the y-axis is a log scale. We have one of those classic exponential growth situations on our hands. And well, what about the evals? Well, I know that there are lies, damned lies, and AI benchmark evals. But to the extent that they're still useful, the evals are certainly showing that open models are right on the heels of closed models, and actually have been for quite some time. And it looks currently like the gap between them is something like 4 months. At least that's what Epic AI, who professionally tracks these guesses. So the verdict that we have to reach, and something that 2025 has like helped to make more clear to us, is that taking AI risk management seriously means taking open weight model risk management seriously. And I think we're starting to get to the point in time where this is a pretty easy sell. But this thesis hasn't like been a broad point of consensus, at least until recently. And maybe it's not like fully adopted yet. And I think that's partially an artifact of like the ecosystem that lots of AI risk management research has been done in and evolved in the past few years. So what I mean by this is like from about 2019 to the beginning of 2025, we were all living in a certain kind of technical regime of advanced AI services where language models were at the top. It was a small number of state-of-the-art models that existed at any given point in time. And they were all from a small number of well-known, well-resourced developers like OpenAI, Anthropic, Google. Meta was probably a distant fourth there, as were some other AI systems from the Chinese ecosystem. But it was really just a small number of closed proprietary models that were on top. And as a result, like the AI risk management community has developed many of its threat models and like invested in a lot of priorities and started to work on a lot of safeguards and tools that are designed for the world in which closed models stay on top. And that's increasingly not becoming the case. And the AI risk management and resource community has pretty convincingly, arguably, been a little bit too slow to adapt maybe to some of the opportunities and risks posed by open models that are distinct from ones posed by closed models. So there's some really good stuff with open models. For example, they diffuse power and influence in the world, and they enable a lot of really useful safety research. And it's difficult to overstate like how very awesome these things are, right? Like personally, I find it kind of hard to imagine a positive AI future without these factors from open models at play. But at the same time, open models make other types of risk management very ecosystemically challenging because they have very complex supply chains and are very difficult to study. The ecosystem around open models is very difficult to study. Open models can spread rapidly, permanently, and globally. No one has any centralized ability to monitor them or mitigate risks from them. Any external safeguard to an open model, like a safety filter, can always be trivially disabled, sometimes by commenting out a single line of code. And finally, open models, perhaps most definingly, are vulnerable to harmful forms of tampering, right? Which is actually like a huge deal because, you know, guaranteed robustness suddenly, at least in theory, just goes away. Like we have no hope of this anymore. Any sort of safeguards that are built into the weights of an open model can always be undone with enough tampering, with enough fine tuning for an actor who is well resourced enough to carry this type of thing out. And because of these challenges that we're like starting to run into in today's, you know, new meta, we're starting to see some pretty acute harms emerge from open models. For example, something that you can do right now, if you're on your laptop, and you should totally try it if you can, go to Hugging Face, go to the model tab, go to the search bar and type in the word uncensored or the word abliterated. And you can find some 7,000 models that have been downloaded, fine-tuned, and uploaded by the community with the explicit goal of removing safeguards against harmful behaviors from inside of them. And one domain in particular that I think we need to pay very close attention to when looking at the risks and harms of open models is the non-consensual AI deepfake porn ecosystem, which I think is starting to become one of the areas in which we're starting to see truly widespread and truly terrible impacts from AI systems at a scale we haven't quite seen before. And this has all kind of been a slow burn since Stable Diffusion was released in 2022. But in 2025, I think things have reached new heights with like the severity of some of these harms, where we're starting to see news articles like this about just how openly and obviously some of these things are affecting large numbers of kids. And this ecosystem is very much built on the back of the open model ecosystem. The Internet Watch Foundation, which is a UK organization who has been monitoring these harms for the past few years, has made the observation that perpetrators continue to use open source models as a tool of choice to generate child sexual abuse material images because access is offline on device, and there are few, if any, opportunities for content moderation and criminal content detection. And in the past few weeks, we now need to put an asterisk on this observation. Anyone remember why? What's been happening in the past few weeks? Grok. So unfortunately, Grok has gotten itself into this game. And we have to plan for that. But admittedly, we need to also acknowledge that this Grok phenomenon was relatively shortly lived, and things got shut down in response to outcry. And I think the Grok phenomenon that we've observed recently with all of the undressings that it did is, you know, as bad as it is only kind of the tip of the iceberg. And I think it got so much attention and it elicited so much backlash because it was so brazenly out in the open, not because the volume of images that had been created by Grok in that time span was particularly large compared to what's underground, and not because the content was particularly bad compared to what's underground. But when it comes to, you know, meaningfully trying to manage risks from these open models, there's a paradigm that we need to kind of glom onto much more than for closed model. So admittedly, like the toolkit for open model safety and closed model safety isn't that different. But one paradigm that really stands out in its importance for open models is making them tamper resistant, making it go from being this difficult to fine tune or modify an open model to do bad things to being like this difficult. And there's some good news and some bad news in this space. Some of the good news is that in the past few years, there's a literature that's kind of popped up around tamper resistant safeguards for open models. I've been a part of this. We did some experiments in the latent adversarial training papers that I didn't talk about, but we've been in this game too. There's other papers as well. These are some of the first papers in the space, but the literature is probably a couple dozen papers in size by now. The bad news is that these safeguards are very, very empirically weak. And just as some of these papers have sprouted up, there's been this other kind of dual literature that's sprouted up on just evaluating how weak they are. And right now, the state of the art for some sort of post-training intervention on a model that tries to make them tamper resistant only gets tamper resistance up to a few dozen and maybe about 200 examples in total, which is not really enough for like data or compute bottlenecks to start really meaningfully restricting people who have the ability to fine-tune models or make Claude code fine-tune models. So this field is somewhat in need of resuscitation, and I want to talk about how we might go about that. Because the way that we've been researching tamper resistance algorithms in the past few years has been thinking inside a particular box or in a particular paradigm. And that is where we start with some sort of LLM, our Smiley-Shoggoth situation. And then we will run some sort of unlearning algorithm, our capability suppression algorithm that requires some retained data, good stuff that we want the model to keep doing, and then gets some removed data, representing bad things that we want the model to stop doing. And we fine tune the model in order to incentivize this and disincentivize this, and bing, bang, boom, we get the result of it. And it's not what we want. Like in practice, what these algorithms tend to do is like give us a little bit of a tamper resistance, but more accurately just kind of make the model safer from a few more angles, rather than really meaningfully resulting in like getting rid of the bad stuff like we might want to. And like I said, like in the state of the art today, there is no paper that has withstood more than 200 adversarial examples of fine tuning from researchers other than the researchers who study it. Does that make sense? Like when someone else has red teamed models, they've always been pretty weak. So maybe in retrospect, using hindsight unapologetically, we can understand why this was maybe always going to fail by looking at how we train models in the first place. And I'm going to look at some numbers for Olmo 2 because they're openly available, but there's no other particular reason we're going to focus on Olmo 2 in this slide. So Olmo 2 was was pre-trained on 5 trillion tokens of web text. It was then instruction fine-tuned on 600 billion tokens of web text. And then when someone like me does a research experiment using the academic GPUs that I have access to, and I run some learning algorithm or something, it usually looks like this. Maybe some of you in the back can't see, but there is a dot there representing about 1 billion tokens of unlearning. And I'm being generous here because oftentimes it's really more like 150 million. And if you stand back and look at this, you might be able to see the problem. And that is that like models learn a lot of stuff from pre-training. And we know that this shapes the concepts and knowledge and behavior that is learned by models, because if it didn't, then we wouldn't train them on this much stuff in the first place. And if there's bad stuff in pre-training, well, it just intuitively seems hard. And it seems true in practice that it's hard for this kind of intervention to really punch above its weight enough to get rid of some of the bad stuff that might have been learned here. So now we need to talk about deep ignorance. So the paper is titled Deep Ignorance, Filtering Pre-Training Data Builds Tamper-Resistant Safeguards into Open-Weight LLMs. And this was the work that I did last year when I had my residency at UKAC. And big credit to Kyle O'Brien, who worked on this together with me. But in this paper, we used some pre-training interventions to advance the state of the art quite a bit on how tamper-resistant open models could be with respect to eliciting harmful biohazard-related capabilities from them. And I was pretty excited that because of how it advanced the state of the art, this paper got some cool attention in news and newsletters. But the main thing that we did is not going to, shock you, but it is easier said than done. Through a lot of trial and error and learning a lot of lessons along the way, we figured out a good way of filtering pre-training data to get rid of enough of it to impair the model's capabilities in the harmful domain. So we ended up introducing a multi-stage filter, which is key to making stuff like this viable. So if you just naively filtered your model's training data with some sort of LLM and you use it as a judge and asked if it's acceptable to include something, that might work fairly well, but you would be using a lot of compute. And pre-training data compute is a huge bottleneck in developing more advanced models. So we need a more efficient way. And the way that we did this at UKAC and Luther was to introduce a multi-stage filtering pipeline, where we would iteratively escalate documents and give them to higher compute but higher reliability filters so that we could most efficiently allocate this filtering budget. And at the end of the day, we were able to do the filtering that we were doing at a cost of 0.8%, the model's overall training budget. So in other words, if you can train a model, you can train a model on filtered data for a domain like this. And the top line result from this paper, the most important thing that we did was comparing a baseline model trained on normal data to a couple of models that we filtered varying amounts of biohazard related content from. So here we have in gray our baseline, in orange our weak filter, in blue our strong filter. And the first thing, as always, sanity check, these models perform comparably well on general capabilities benchmarks. But when we start tampering with them adversarially, this is where we get the good news. And so these models off the shelf start off quite bio-ignorant like we want them to be. And they only slowly gain bio-related capabilities over time as we fine-tune on a data set of biohazard-related content. And it takes about 300 million fine-tuning tokens, which was the equivalent to 10,000 adversarial fine-tuning steps to get this blue curve up to about the point that the gray curve started at. And how does this compare to prior states of the art post-training safeguards? Well, we tested a technique called circuit breaking, which has been near the state of the art empirically. And we also added latent adversarial training to it because I'm the latent adversarial training guy. And what we found is that these safeguards folded after just a few hundred steps under our setup, while the filtering was much more enduring. And here's another result that I think is very important, but is not going to surprise you. Our particular filtering approach resulted in models that were completely robust to tampering on non-biohazard data, to benign tampering, which, like, of course it would be. Like, if it didn't learn about the bio, it's not going to learn about bio when you train it on something other than bio. But the nice thing about this is that in the tamper resistance literature in the space, this is the first technique that is fully robust to benign fine-tuning, because every other post-training safeguard tends to like go away slowly as you just fine-tune the model even on benign data. And now we're going to fast forward to when I finished at UKAC. I went back to MIT. The first thing I worked on this fall was an open problems paper to try to incubate the field of open weight model risk management research and try to lay out some open problems that we can do more work on. So I got together a really talented group of authors, which I'm very thankful for. And we talked about 16 open problems involving open weight model risk management, 6 of my favorites of which I'll talk to you here about. And I'm excited about doing some work on this in the next few months and years. One thing that I'm interested in could be deepening safeguards by running unlearning algorithms doing pre-training. Another could be scaling unlearning interventions, right? Trying to make that like orange dot a lot bigger. We can also try to mechanistically understand what deep ignorance might look like and then use it to improve tamper-resistant unlearning algorithms. Because most of these unlearning algorithms have very improvable loss functions. Another thing we can do is power up adversarial training under diverse tampering threats. And then finally, do more standardized evaluation suites for tamper resistance. This is a little bit what I was talking about, like with what Hugging Face might be able to do, for example. And I'm very excited about this type of work in the future. I'm excited to work with academics, but also governments on it, because governments are increasingly realizing that open weight models might start soon posing pretty credible security risks. And an example of this, hashtag not an ad, but I told Andrew at AC that I would pub for him this open job position that they have. So if you are a research scientist interested in working on open source technical safeguards, send me a message so I can connect you with Andrew. And now we're at another checkpoint. So how do we feel about open model safety, about deep ignorance, about data filtering and pre-training methods? Any questions?
Yeah, so I wonder whether tamper resistance is like a finger in the dike. Like somebody's going to be selling a black market model that hasn't been safety tuned at all.
Yeah. So there are 2 thoughts I have on this matter. And we'll get into a little bit of this more in a couple slides. But one is that if there is one model out there that really undercuts the effectiveness of safety mitigations throughout the ecosystem, right? Like you said, if someone fine-tunes something terrible and it gets out somehow, that's a big problem. It's like the finger in the dike kind of situation. But another idea that I think is important to emphasize in tension with this idea is that the AI ecosystem or sub-ecosystems inside of it are not just as safe as the least safe systems inside of it, right? Like, because that idea, is an easy one to kind of assume in some conversations, but if we assume that the ecosystem is only as safe as the least safe system inside of it, the bar starts low and it goes lower forever. And it's just kind of a race to the bottom. Mm-hmm. And the amount by which making something less accessible or making something more marginalized helps us with safety is going to vary a lot by field. Imagine you're Anthropic and on the heels of last year's big incident involving this kind of thing, you're trying to make a you're trying to mitigate risks involving state actors using your models for cyber attacks. Right? If it's state actors you're up against, you really kind of need to plug all the holes, right? Because if there's something out there, you'll probably find it.
Yep.
On the other hand, if you're working on like in the other side of the spectrum, if you're working in mitigating CSAM from AI systems, accessibility, I think, starts to matter a lot in a part of the ecosystem where an extremely large fraction of the perpetrators are teenagers. So mitigations matter. That's my response to it. But they will matter. Mitigations in an ecosystem will matter to very different degrees in different fields, depending on kind of what the threats are. That's a good question. Yeah.
Kind of a related question. To what extent are creators of open weight models incentivized to actually implement technical safeguards? So you can imagine with an API-based system, there's been lawsuits against OpenAI versus because of uses of their model and sort of not quite been established, but at least some direction that API-based providers are to some extent liable for how people use their systems. But that seems like a much harder leap to make for open source models. So in that case, are you really just relying on the goodwill of people not wanting their models to be used for some evil case, or is there a way to actually incentivize it?
Yeah. So I'm really happy with the questions you're asking, but you're also spoiling my slides later. So
Okay. I can wait.
1:30 is.
yeah, we'll be able to finish on time. But part of the answer is there are two kind of reasons to work on AI safeguards. And one of these reasons is that we can build a toolbox and understand it well, and then it can be voluntarily used by developers and actors in the ecosystem who care about voluntarily doing that kind of thing. This is not generally the case. Remember, we were talking about what happened with Grok recently. Go look at Elon Musk's tweets. You'll be disappointed about how he views this issue, for example. In contrast to relying on voluntary adoption, I think my much greater reason for doing the type of safeguards the work that I do is because building that toolbox is a prerequisite to ever holding anyone accountable to using it. So I'll talk more in the next few slides about how researchers like me, I think, need to think a lot more about studying accountability and standards and supporting lawsuits and doing stuff like this in the real world. We'll get to more of it. And I was going to do a bit and you kind of ruined it, but I'm going to still do the bit. So I was going to talk about how I'm very excited about making more progress on open model risk management and how 2026 is going to be a big year for this. And there's a lot of low and medium hanging fruit, and there's a ton of progress to make, and I'm super stoked about it. And all of that is true. And then the bit was going to be to say, and as you know, once we do all of that, all of our problems with AI are going to be solved. And then everyone's just going to be like, what the hell, Cass? And then I was going to be like, okay, no, there actually are some other problems to solve. And it's the most unsolvable problems of them all. The ones that involve engaging real people and real institutions in the real messy, complex world that we all live in. It ain't January 2025 anymore. So the safety toolkit only matters if it is used. And I think this is trivial to understand, but I think it's become a more poignantly recognizable point in the past year or so. We can look at some recent high-profile, big AI safety incidents that have started to happen recently, in 2025. Remember back in the spring and summer when ChatGPT was sycophantic to the point of being a suicide coach? And who could forget when Grok was a Nazi? Just literally was a Nazi for a while. And I look at these problems and these real world AI safety failures that are starting to happen, and I find it very frustrating. And not just because they're bad. But some of you can maybe relate to me here. Don't you just look at these issues and does a part of you deep down just sort of maybe wish that if AI was going to fail in the real world like this, it would at least be kind of interesting? Because these are not complex failure modes, right? There's no agent in either of these cases accomplishing a complex task. There's no adversarial attacker at play. There's no treacherous left turn or deception involved or anything. It's just straight up sycophancy on the left and just praising Hitler on the right. I don't know how more simply you can put it than that. And in practice, it was supervised fine-tuning and prompting that were both the causes and the solutions to these types of problems. And if you're doing the research you're doing on trustworthy AI in 2026 or AI safeguards in 2026, you're up here, right? You're working on problems that are new and interesting and non-trivial and worth making more progress on and to push the bounds of human like knowledge, these problems are down here. This stuff is kind of like what we were supposed to have like figured out in 2020. So there's this annoying emerging trend for lots of our biggest AI safety incidents in the real world to be things that actually kind of have solutions, just solutions that we're failing to implement. And I want to go back and look once more at my favorite / least favorite thing to study, or sub-ecosystem in AI to study. And that is the technical ecosystem behind the creation of non-consensual AI personalized deepfake porn. And actually, the most recent project that I finished and put online with a co-author of mine named Max, who's great, is titled Video Deepfake Abuse, How Company Choices Predictably Shape Misuse Patterns. And there's a lot that we found in this paper, but I'm going to go over it quickly because none of it is probably going to surprise you that much. One thing that we observed is that in the malicious technical ecosystem behind some of these harmful capabilities, model developers are a really critical node, and they're a very narrow bottleneck. And indeed, in the real world, we find that it's a very small number of models that tends to get used the most from a small number of developers for the creation of this type of content online. Meanwhile, there are solutions, there are mitigations that exist and matter, and we know this from the research on them, and we also know it from looking at the empirical usage in creating this type of content from models that do versus don't have safeguards like data filtration. And finally, and maybe most frustratingly of all, is that developers really don't report that much on risks or any mitigations, let alone address them, at least to public knowledge. So we have this problem, this ecosystem, this big AI issue that's starting to affect, well, has been affecting people for a while, but is really kind of like, hitting new heights in terms of its severity every year and affecting a lot of kids out there. And we know that the harms are foreseeable from a developer's perspective. We know that they're mitigatable from a developer's perspective, and we know that mitigations matter in an ecosystem where so many of the perpetrators are literally just teenagers who get onto like a Discord or Telegram. This is kind of a case study, though, in an ecosystem that, despite all of those things, is very unhealthy in the AI space. So now, finally, it's about time. We need to talk about this guy. So last year, well, in 2024 and 2025, almost every US state passed some sort of law making it some sort of criminal offense to non-consensually create an AI deepfake depicting another person's likeness in a pornographic context, or to share something like that. That is not remarkable, because like in terms of like states getting involved in this kind of stuff, Arkansas in the US was a state who did this exact thing. But Arkansas also did something else. They passed HB 1529, which modified State Act 827. This was enacted in April of last year. This is what that bill looks like. It's 2.5 pages. You can all go look at it if you want. But there's one section of it, section 2, that we need to pay close attention to. And as a legal mechanism or a bill that was passed in the United States, this at this point in time is extremely unique. Section 2, the Attorney General may institute a civil action on behalf of the state against a provider or developer of image generation technology that was used to create deepfake visual material in violation of state code if the provider or developer of the image generation technology did not have reasonable safeguards in place to protect against the generation of deepfake visual material. So in other words, if you are a developer and you fail to take reasonable safeguards against mitigating deepfake risks, and your model is used downstream predictably to cause harm to people in Arkansas, this guy, Arkansas Attorney General Tim Griffin, can take civil action against you in court. And this is where accountability mechanisms come in. And this is where technical people are going to be needed to understand what reasonable safeguards are. So after we finished our project, Max and I emailed a few state officials in different states where interesting debates were going on, including in Arkansas. And we got a chance to talk to a couple people under Tim in the Attorney General's office. And we told them what we found and how they might want to take a close look at what Civitai and Alibaba and Twitter are doing. And they said that, if the case is there, they would love to be the Attorney General's office in 2026 to hold developers accountable for these types of things. So that's why I'm keeping an extremely close eye on Tim Griffin this year, and why I think you should too. And slightly more broadly, this has got me thinking very seriously about whether some of the most interesting and useful work that someone who works on AI safeguards like I do is going to increasingly in the next few years involve not necessarily like pushing robustness frontiers, but also involve looking at the real relationships between the choices that companies make and the downstream harms of them, looking at safeguards in the wild. And I'm thinking a lot about this, and if you're thinking about similar things, we should talk sometime. So it's about time to wrap up, and how do I want to end this? There are a few ideas that I hope I've left you with that you can chew on, and that maybe we can talk about. My email address is here. One of them is that safety failures of state-of-the-art LLMs are frustratingly persistent in the real world. Another is that how possible solution to this, or partial solution, is to create over-engineered safeguards. Take some inspiration from the light folks. And the model tampering attacks can help you power up adversarial training and testing. That open weight models are becoming one of the most important and interesting frontiers for AI safeguard research. That tamper resistance can help with open models and can be aided by deep ignorance. And then finally, that from now on, some of the most interesting and important research to work on AI safeguards is likely to involve empirically studying how, if and how safeguards are effectively used in production systems. And that is the prerequisite to ever holding anyone accountable via any standards framework or via any liability incentive to making systems that are safe in the real world. So if you're thinking about anything similar, we should talk. And it's 1:31. So if anyone wants to stay a little bit after for questions, or I'm just happy to talk about anything more. Thanks so much.
Yeah, I think there is another meeting here at 1:30, so
I'll take the pizza and run. Also take my email address too. Thanks, Eric.